Hello, welcome to Chapter 7, Section 4, on the concentration of a solution. The concentration of a solution is basically telling us how much solute is present in our solution. This is very important. In the lab, you have solutions that could be 1 molar concentration or 2.0 molar concentration. And there's different ways that we can express concentration. So that's what we're going to focus on, are the calculations and the ways, or the units of concentration. And we're going to look at mass percent, M over M, volume percent, V over V, mass volume percent. So these are going to be just our units. You have to have units of mass or volume, depending on which one you're using. And then molarity. Molarity is moles of solute over liters of solution. So these are the 4 ways that for your class you're going to be able to express concentration. And basically it's only different by its units. They just have different units. But we're still looking at how much solute is present in the amount of solution. The first one we're going to look at is mass percent, or percent by mass. You also hear it referred to as that, is the concentration by mass. Your key here is mass percent. This means that your units in your numerator and denominator are going to be grams consistently when you use mass percent. So you have grams of the solute over the total grams of the solute plus grams of the solvent. Okay, and so we use mass percent, and we multiply this times 100 because we're considering it to be out of a 100-gram solution. So here, if we were to add 8 grams of KCl to an amount of water that weighs 50 grams. So this is showing what you might do in labs. To add 8 grams, that's the KCl, potassium chloride, that's the white solid, to the water. So we want to calculate the mass percent. And so we would take the grams of solute, so that was 8 grams, and we're going to divide it by the mass, or the grams of the total solution. So the key here is that you remember that it's the total mass of the solution. Okay? So we have 8 grams of solute, and we had our 42 grams of solvent. This adds together to give us 50 grams. Okay, so we look back here, this makes sense as well. We started with the water, added 8 grams, and we ended up with 50 as our total mass. This is what you would actually do in the lab. Okay, so you take grams of the solute, which was 8, and you divide it by 50, so right here. That's the total mass of the solution, 8 plus 42. And you multiply this times 100, and this would give you 16% mass percent of KCl in the water. Okay, so let's work a practice problem. We have 15 grams of sodium carbonate and 235 grams of water. Calculate the mass percent. Okay, so mass percent equal to grams of solute. Anytime you see water, it's pretty much 99.9% of the time going to be your solvent. And then over the grams of the total solution. So you could even write that. It helps you remember. So if we have 15 grams, you got to first recognize this is our solute. It's present in the least amount, divided by the total grams of the solution. Okay, so we have 15 grams of solute plus we have 235 grams of water. So 15 and 35 gives us 250. So we would put 250 grams times 100. So if we divide 15 by 250 times 100, we should end up with C, 6.00% mass of our solute. This is the percentage of our solute, which is sodium carbonate in this situation, that is in our solution. For volume percent, this is exactly what it states here, is we are going to have a volume unit over another volume unit. You have to be sure that your units match, so we're going to use milliliters here. But the percent by volume of a solute over the volume of a solution. So you just take your volume divided by your volume of the total solution times 100. Okay, and so you can also look at, if you were to use this in a conversion factor type scenario, you would have, we always consider, because we're multiplying times 100, we're considering that we have so many milliliters of solute out of 100 milliliters of solution. So we're basing these off of 100. So here is an example of volume percent. And we're given two volumes, one of our solute, which is HCl, hydrochloric acid, and the final solution volume of 140. This is where you want to be careful to be sure and recognize what the problem is giving you. And it is telling us here that we have a final solution volume of 140. Okay, so we're not going to have to add the 20 mils here to our final solution, our total solution. Okay, so if we take our 20 milliliters and divide it by, we want to divide it by the total volume. Okay, well, our problem is telling us that the final solution volume is 140. So in this case, we do not add 140 plus 20. We don't add that solute in there because it's already telling us the final volume. It's telling us the total volume. So if we divide 20 by 140 times 100, we get about 14% HCl volume percent. Our third way, so that was our second, to label that, but our third way to express concentration is mass volume. Okay, so we've looked at mass, so we have to use grams over grams times 100. We've looked at now volume, so we have milliliters over milliliters times 100. And each time it's like almost like part over whole. You're taking part, because we know that the solute's the smaller amount, over the whole solution times 100. So this time, mass volume, you can probably already guess, is going to be the percent by mass of the solute to the volume of the solution. So our units are here, they're grams over milliliters. So we take grams of solute and divide it by the milliliters of solution. And once again, if we were to set up a conversion factor, I'm actually not going to have you guys do a lot of calculations with these. We have omitted the page 263, the using concentrations as conversion factors. So that's where that's kind of leading into. But we would do this the same way. We would take the grams of our solute, and then we take it over the milliliters of the total solution. So here is already telling us mass over volume, so grams over milliliters times 100. An example here would look just like, or very similar to our other examples. If we were using our mass volume percent, that's what we're trying to find. What is the mass volume percent of the KCl solution? So we know that mass volume goes ahead and tells us it's going to be mass over volume times 100. That's our percentage. We're going to take the mass of our solute. Okay, remember solute goes on top. Divided by the total volume of the solution. And so here we're given the final volume. We're given that already. We don't have to add anything to that. Okay. So if we take 5 divided by 250 times 100, we get a 2.0% mass volume KCl solution. Like the C there. Sorry about that. That looks really bad. The fourth way to express, sorry about that, to express concentration is by molarity. This is probably the most popular way, and it includes molarity is equal to moles of solute divided by liters of solution. So this time we've got moles. Everybody has to remember moles are, we have to be able to convert in some of these problems from grams to moles. So that's our key here. We've been using grams, now we're going to be using moles. And per the volume of the solution. So molarity is given the symbol big M, just like this. And we also use it in saying, so if we say we have a 1 molar or 1 molarity sodium chloride solution. Okay, when we have a 1 molar NaCl solution, it's going to look like this. We're going to have 1 mole of NaCl, and we're going to add it to 1 liter of a solution, because 1 over 1, so molarity is equal to 1 mole over 1 liter gives us 1. But this is a very popular way of expressing concentration. Okay. We want to know what the molarity of a 0.500, so we have half a liter of NaOH solution if it contains 6 grams of NaOH. Okay, molarity, you want to commit this to memory, is moles of solute per liter of solution. Okay, so really we have, well, we have 3 variables, but we have to be given, 2 of the 3 to solve. So we're solving for molarity. We're going to leave our equation as it is, and we have to plug in for moles. Okay, well, we've got a problem. We're given grams, so we know we're going to have to convert from grams to moles. Okay, and we're given liters, which is good. So we could go ahead and say, okay, we've got 0.500 liter of an NaOH solution. So we already have our denominator. That's our variable we can plug in there. Okay. The next thing we have to do before we can move on is we have to convert from grams to moles. So you have to remember this from the past chapters where we have taken 6 grams of NaOH and we convert to moles. So our grams have to cancel. Okay. 40 comes from the periodic table. So if you look at your periodic table and you add up the molar mass of sodium, oxygen, hydrogen, so this is the molar mass, we get 40. And we place it in the denominator because we have to have our units cancel. Our grams of NaOH have to cancel, and we're left with moles on top. So this is what we are looking for. So this gives us 0.150 moles of NaOH. All right, so we've already written out the concentration expression, or I did on the previous slide. And so now we have to substitute these in. We've already put in our liters, and we found our moles on the previous slide. And if we divide 0.150 by 0.500, we get a 0.300 molar, or molarity, NaOH, sodium hydroxide solution. One more example for molarity, to be sure everyone's got this. We want to find the molarity of potassium nitrate solution. Okay. And we know the molarity, moles of solute per liter of solution. We're given that we have 34.8 grams. And we're given the liters of solution. Okay, so we can go ahead and plug in 0.225 liters, but we're given grams. We've got to convert from grams to moles. Okay, so if we use our periodic table and we add up the molar mass of KNO3, okay, and we see that potassium should get about 101.1. Sorry for the interruption. I'm going to go ahead and add that up. So if you look at your periodic table, you should get the molar mass of potassium, nitrogen, and 3 oxygen should be about 101.1. So our grams will cancel, and we're left with our moles on top. This gives us about 0.344 moles KNO3. Okay? So now if you want to go from here, and we plug in our moles, so all we had to do is go from grams to moles. We're going to get about 1.53 molar KNO3 solution. Don't forget what this is telling us. This is telling us how much solute is present in our container, or it could be in our reaction, and this becomes very important to chemists. There are reactions that you can only use, a specific molarity, or the whole reaction will not go according to what is desired. So these are the 4 ways that you guys will need to know how to express concentration.